Let me start by echoing what various speakers have already said before. Big thanks to the organizers for putting together strings here at CERN, and also for inviting me to talk. I'm very happy to be telling you about recent results that appeared a few months ago and work in progress, together with two amazing collaborators. Logarithmic, who is one of the foremost experts on the topic. Better? So Logarithmic is one of the foremost experts on the topic of asymptotic symmetries and soft theorems, among other things, and my outstanding postdoc, Sang-Min Choi, who has been the powerful driving force behind this collaboration. And aspects of what I'm going to discuss are also related to earlier and ongoing work, together with my student Diogo Pano, and my current and former postdocs, Prahar Mitra and Emilio Trevisani. So the context of this talk is in this big question: what are all the symmetries of nature? And for the purpose of this talk, I'm going to approximate our world by a vanishing cosmological constant. And I guess since we're at CERN here, people here would be OK with that. So I can go on. So over the past decades, we have learned a great amount about gauge theories and gravity in four space-time dimensions, and in particular that they have a very rich infrared structure. In particular, there are infinite dimensional symmetries underlying dynamical processes. Indeed, infrared divergences of the conventional S matrix can be viewed as arising from a violation of the conservation laws associated with these symmetries. And so one of the immediate questions here is, can we identify all these symmetries that arise from the physics in the infrared, so at large distances or low energy? And identifying all the symmetries is an important problem in its own right, but it is also one of the cornerstones for formulating a holographic principle. And the holographic principle for the context of this talk will be one for asymptotically flat spacetimes. More specifically, the proposed holographic principle that will relate to this talk is one called celestial holography. It suggests that quantum gravity in four-dimensional asymptotically flat spacetimes may have a dual description in terms of a two-dimensional theory living on the celestial sphere. And this theory appears to have some features that look like conformal field theories, and so for that purpose, we will refer to it as celestial CFT. There are two immediate hints that suggest that such holographic duality may be at work. The first arises from considerations of symmetry. So it's a fact that Lorentz symmetry in d+2 space-time dimensions acts on the celestial sphere at the boundary as the Euclidean conformal group in d dimensions. And so we sort of automatically get global conformal symmetry in this putative holographic dual theory. The second hint comes from looking at observables in asymptotically flat space. So that's the S matrix. And usually we discuss it in an energy basis where translation symmetry is made manifest. This is not a very suitable observable or version of this observable for the purpose of holographic questions. Instead, a more natural observable are the so-called celestial amplitudes, which are nothing but the S matrix expressed in a different basis. So this basis is a boost weight basis, which can be obtained from the usual energy basis by a Mellin transform over the energies, introducing in that way the boost weight. Now, these celestial amplitudes, they look like correlation functions in a conformal field theory. They make the bulk Lorentz symmetry manifest, and therefore nicely transform under global conformal transformations on the sphere. But if you want to say that there's a two-dimensional conformal field theory at the boundary, global conformal symmetry is not enough. We need local conformal symmetry, so an infinite enhancement. And where's that coming from? I also told you that there is a lot of infinite dimensional symmetries from the infrared in asymptotically flat space. So potentially we have more symmetries, and they all have to appear in some form or other on the celestial sphere infinity. So the way this shows up is what's called asymptotic symmetries. So these are large gauge transformations or diffeomorphisms that preserve the boundary conditions imposed on the field, so for example the metric. So they preserve the large distance fall-offs. So in gravity, when we go near the boundary, we demand that the spacetime is flat asymptotically, but then they're 1/r corrections because we're actually in quantum gravity. And these 1/r corrections, they contain information about the mass aspect and the angular momentum aspect in the space-time. And I've particularly highlighted here one of the subleading terms in the angular metric component, which is the shear, which carries information about gravitational waves. Now, what are the asymptotic symmetries of such spacetimes that are asymptotically flat with some prescribed boundary conditions that I was hiding in a ... What you have to do is you have to find all the diffeomorphism vector fields psi such that the leader derivative on the metric vanishes asymptotically at large distances, or rather in such a way that these boundary conditions, these fall-offs, are preserved. And unlike gauge redundancies, asymptotic symmetries actually act non-trivially on the physical data at the boundary and give rise to non-zero charges. Now, the most famous asymptotic symmetries are the so-called BMS supertranslations. You might think that as you go to large distances, gravity becomes weak, and so the symmetry group that you recover is Poincaré, but that's actually not so. You get instead an infinite enhancement of translations. So, for example, rather than just having global retarded time translations on the boundary, you get a whole function worth of transformations, each one for each point or angle direction on the sphere. And this is the famous BMS group. Now, supertranslations are one side of the same infrared coin, or rather one corner of a triangle of relations. The other two corners being the so-called displacement memory effect in gravity, and the third one being the so-called soft graviton theorem, which is a factorization property of scattering amplitudes that we have also just heard about, where you take the energy of an external massless particle, in this case the graviton, to 0, and then the amplitude factorizes into the lower point amplitude without that soft particle, multiplied by a factor and a pole in the energy. Now, this is a low energy expansion. They're ... here. And the next one in these ... is the subleadings of graviton theorem, which was discovered much later, which comes with a constant in the energy behavior. And this one has its own memory effect and also has an asymptotic symmetry interpretation. And that one is a local enhancement of Lorentz symmetry called superrotations. And this is precisely the local enhancement of the global conformal symmetry on the celestial sphere. And so just what we need to go towards a statement that there may be a conformal field theory living on the sphere. Now, there's other infrared relations beyond gravity. So in QED or scalar QED, there's a soft photon theorem, its own memory effect related to that, and a symmetry interpretation, which you may refer to as superphase rotations. There is non-abelian versions, there's supersymmetric versions, and so on. If you restrict to a suitable projected version of the S matrix, then you may even extract some universal features of a whole infinite tower in this infinite soft expansion. And for the whole purpose of discussing all these different infrared aspects here, it is very useful to consider different languages. So for soft theorems, we usually use an energy basis. For the memory effects, we use a position basis. In particular, we use retarded time at the future boundary. And these are, of course, related by a Fourier transform. And then the boost weight basis can be obtained from either one of those by integrating over either energy or the retarded time coordinate. And the boost weight basis has the feature that it makes particular aspects of symmetry manifest. So we could imagine just sitting on the celestial sphere, the two-dimensional celestial sphere, and forgetting about what happens in the bulk and just trying to understand what kind of symmetries we would expect in such a theory using general principles. So the input here is conformal representation theory, from which we will derive what the operators are that are associated with symmetries. The name of the game here is to find all the conformal multiplets containing symmetry operators and then seeing how these conformal multiplets terminate. They terminate when a descendant of a special primary operator that is associated to symmetries becomes a primary itself. And that gives the conservation equation for this primary operator that has to do with symmetry. Now, explicitly constructing such operators, say in gravity, for conformal dimensions of boost weights 1 and 0, shows that these operators actually generate the extended BMS symmetries. So supertranslations and superrotations, just from a 2D perspective. Moreover, you can classify all the special symmetry operators in this putative celestial conformal field theory both in 2 dimensions and in general dimensions. And there you will add a semi-infinite list of operators starting at dimension -1 all the way to -infinity. What's remarkable about this list of infinite operators is that they satisfy an infinite dimensional algebra. And in gravity, this is the W1 plus infinity algebra that has appeared much earlier in Penrose's twistor construction. So from this perspective, we seem to get the statement that there may be an infinite dimensional symmetry algebra in asymptotical flat space, of which the local conformal symmetry is part of. However, the statements that I made before, stating that soft theorems have these asymptotic symmetries built in, was a statement at tree level. What happens at loop level? So there has been some progress in understanding what the symmetries of the S matrix are at loop level, but a first principles derivation of that has remained elusive. Moreover, it is important to stress that here we're not talking just about quantum effects on top of tree-level statements. Actually, the long-range infrared interactions in gauge theory and gravity, they even modify the classical statements. And this is seminal work by Alok Lada and Ashok Sen, who found that there are logarithmic terms in the soft energy expansion. And these logarithmic terms in the energy, they render ambiguous all the sub-leading tree-level soft theorems. And later on, Sahu Sen, Saha, and Sahu Sen, they found that there are actually novel soft theorems related to these logarithms. And so if we want to say the S matrix has a large amount of asymptotic symmetries, the statement should be made for the loop-corrected and log-corrected soft theorems. So in order to do that, let me go into a little bit more detail. So at tree level, we have a soft expansion of the S matrix that includes powers of the energy. The leading term here is the famous Weinberg pole. That one is tree-level exact and universal, so it only depends on the momentum of the hard particles. In gravity, at sub-leading order in the soft expansion, you also get a term that's universal, but it is loop-corrected. And so are all the further sub-leading terms in the soft expansion, and moreover, you pick up non-universal expressions. Now, if you take into account the long-range interactions of gauge theory and gravity, you arrive at new soft theorems, which now also have logarithms in the energy. The leading one remains unaffected, but at sub-leading order, this modification kicks in. The sub-leading factor that multiplies now a logarithm in the energy turns out to be one loop exact and also universal. And so now the question is the universality of these new logarithmic soft theorems a consequence of some asymptotic symmetry of the S matrix? And so this is what I want to tell you. So if you want to establish a symmetry interpretation for a soft theorem from first principles, what we will do is we're going to use the covariant phase space formalism for an asymptotic symmetry transformation delta, from which we compute charges, q plus and minus, and the conservation of these charges from the past boundary to the future boundary should land us on the desired soft theorem. So this is the strategy. So in order to compute the symplectic structure, this is an object that is defined on a Cauchy slice, but we have to push it to the boundary. So there's a piece on the future null boundary, for which it is convenient to use retarded Bondi coordinates. And the null boundary is obtained by taking the radial coordinate to infinity while keeping the retarded time u fixed. There's another piece, which is time like infinity. And that's a bit more tricky because in this Penrose compactification, this is just a point. And so if you want to properly describe the decay of massive matter, we need to blow it up. So this is conveniently done by using Euclidean ADS3 coordinates, which provide us with this hyperbolic slicing of the interior of the light cone in Minkowski space. And in order to push all of this to the future time-like boundary, what we have to do is to take this time coordinate tau to infinity while keeping this coordinate rho fixed. Once we have computed the symplectic structure in that way, we can then try to extract from that a charge. This will have two pieces, one coming from the null boundary and the other coming from the time-like boundary. And these two pieces have the name soft and hard charge, And this comes from how they should arise in the context of relating this to soft theorems. So the soft charge is expected to correspond to the soft insertion of a soft photon or a soft graviton, while the hard charge should implement the action of the symmetry on the hard matter particles. And this should, in the end, turn into this soft factor multiplying the energy dependence in the amplitude. So let's do this for gravity. So we're going to consider an effective quantum theory of linear metric perturbations, H, and a minimally coupled massive real scale field phi. So we want to extract from the covariant phase space a conservation law that lands us on the soft theorem. So what is the soft factor here that we have to match onto? So the leading soft factor that multiplies this pole is this universal piece I mentioned before. Depends just on the momenta of the hard particles. At tree level, there is a subleading term multiplying energy to the 0, which is also universal, just depends on momenta and angular momenta of the hard particles. But remember, in the presence of long-range interactions, these tree-level soft theorems become ambiguous. So we should look at the logarithmic soft theorem, whose factor is much more complicated. And this is the work by Sahu Sen and Sahu Sen. So there is classical and quantum contributions to the soft factor. Let me first discuss the classical piece. So this comes from the late-time gravitational radiation that's due to the particle acceleration because of the long-range gravitational interactions. There's an analogous quantum piece where the range of the loop momentum is between the soft energy scale and the energy scale of the other hard particles. And then what I have not written on this slide here are additional terms that are related to the drag of the soft graviton, and which I will get back to later. So I'm going to focus on this classical logarithmic soft graviton theorem in the next couple of slides. So in order to compute or extract the charge conservation law, we need two ingredients. First, we have to decide what the symmetry should be. And second, we have to look at what the fall-offs of the metric and the scalar field are. Let me start with the symmetry interpretation. So we expect local conformal symmetry to persist. And so we're going to start by looking at transformations that correspond to superrotations on the boundary. Now, at the null boundary, superrotations are characterized by a vector field y, which implements the superrotation by acting with this leader derivative on the metric. And at time like infinity, we also have a vector field, now y bar, which acts on the matter scalar fields in that way. And we can relate the superrotation at the time-like boundary to the one at the null boundary by this vector Green's function. And in this way, we can identify a superrotation vector field that is smooth across both pieces of the null boundary. Now, we need a second piece, which is the fall-offs of the fields. So at null infinity, we have to look at the fall-off of the metric. There's a subleading piece of the angular part that I've discussed before, the shear. And its leading piece is constant in R, but has this large time behavior. So there's a piece that is constant in time, and that piece is ultimately related to the gravitational displacement memory effect. There's another piece here, which goes like 1 over time, the null time. And this piece here will be related to the tail memory effect, in addition to this displacement memory. At the time-like boundary, we get, because of the matter stress tensor, we get a component of the metric that has a similarly looking behavior. There's also a 1 over time piece. And this 1 over time piece here is related to logarithms that appear in the asymptotic expansion of the matter field. And this essentially comes from the fact that matter, in the presence of gravity, get dressed. And so this logarithm comes from the stressing factor. And what I highlighted in blue is what happens if you take into account the long-range interactions of gravity. So now we can put this together and compute the symplectic structure with these two pieces. Turns out that the symplectic structure diverges logarithmically at late times. And we will regulate this by introducing a late time cutoff. So this is an infrared cutoff at late times that is associated to this physical effect that we have long-range interactions. So this lands us then on a regularized Noether charge, which has two pieces. One multiplies the logarithm of the cutoff, and then a finite piece. And these are the explicit expressions. So you can see that the hard charges, so the first line here, of these two expressions are different. But I want to point out that the soft charges between these two pieces are rather similar, except for these projectors in U. And we'll come back to that in a moment. So now we have constructed this charge from a covariant phase space. Now we have to see if this has anything to do with soft theorems. So let's look first at this finite piece here. It turns out that if you make a suitable identifications of fields between the past and the future boundary, then you can come up with a conservation law for this finite piece. And this conservation law is actually one that was considered already a decade ago and led to the connection between asymptotic symmetries, superrotations, and the tree-level subleadings of graviton theorem. But remember that infrared effects render subleading tree-level soft theorems ambiguous. And so this is not the one that we want to relate to these novel soft theorems. Instead, let's see if the first piece that multiplies the logarithm in the cutoff does this job. Again, you can come up with a conservation law between the past and the future boundary of this logarithmic charge. And lo and behold, this is precisely the classical logarithmic soft graviton theorem of Sahu-Sen and Saha-Sahu-Sen. And so now this establishes really a symmetry interpretation of these logarithmic soft theorems. And it says that superrotations are really a symmetry of the S matrix, even in the presence of long-range infrared interactions. Now, OK, I think I'm out of time. That was the sign. 5 minutes, OK. I saw the flag here. OK, so let me come back to this statement about the soft part of the charges. So I emphasized that between the tree level and the new logarithmic charge, the only really difference that we see here is a different projector acting on the soft insertion, which is this shear part here. And this is actually precisely what we need. Because remember, in the momentum basis, we had to replace a piece that was constant in the energy by a piece that was logarithmic in the energy. And this projector in U is just the Fourier transform version of this statement. Now, we could have also gotten a guide from these boost bases as to whether the superrotation symmetry should really remain in the presence of long-range interactions. And this comes from this classification of symmetry operators in celestial conformal field theory. So at tree level, we have this expansion in powers of the energy, which for celestial amplitudes maps to the statement that there are poles in these correlators that appear at certain integer values of the boost weight. And these poles are simple poles. If you now add logarithmic dependence in the energy, then these will turn into higher order poles of these correlation functions. But the values in the boost weight at which these appear are precisely the same as all these tree-level subleading symmetry generators that we had discussed. And so from this perspective, you should already have had in mind that the symmetries should persist at the loop level. OK, now a final comment about these extra terms that I didn't explicitly write in the soft factor. So there are new terms in the soft graviton factor that come from the gravitational drag on the soft graviton due to the presence of finite energy particles. And a way to think about this is by defining a new retarded time at the detector, which has an extra logarithmic piece in the radial coordinate and gets multiplied by something that depends on a matter content at the future boundary. And we see these drag terms from our covariant phase space approach because they arise in the form of some infrared divergence of the symplectic structure. And sometimes when we have divergences in a symplectic structure, we can subtract them. But here we cannot because they depend on this matter content at the future boundary. So we also looked at the logarithmic soft photon theorem in scalar QED. There I will just give the summary. A similar story goes through. An important difference is that the symmetry transformations, so the superphase rotations that you have to consider, are now divergent. So you have to allow for divergences in R and in U in order to make a statement about symmetries of the S matrix. And once you have dealt with that, you land at a very similar statement as in gravity. In particular, the logarithmic soft photon theorem really arises from a conservation law of a regularized version of the charges that arise in the covariant phase space approach. So we have shown that logarithmic soft theorems have a symmetry interpretation. And the approach that we took from the covariant phase space was a first principles one. It gave us a clear split between tree-level and law-corrected statements. We used a regulator that was tied to the relevant infrared physics, maybe the ones at late time. And we can remove the regulator in the end and end up with finite observables. So this is a symmetry interpretation for the S matrix. So to summarize, asymptotic or soft symmetries encode universal, large distance, low energy physics. The celestial boost spaces is useful for making some aspects manifest and for serving as a guide. And while identification of symmetries is important in its own right, it's really key for the holographic principle. And we have put on firmer footing some of the symmetries that arise in asymptotically flat space. Let me end here with one outstanding question, which I think is super interesting, which is that there are more than this first logarithmic soft theorem that I discussed, which has universal features. Potentially, there is a whole tower of universal or loop-exact logarithmic soft theorems. And now the question is, how many infinities of symmetries do we really have in the sky? Thank you.
Thank you very much for a great lecture. Any questions or comments? Yeah, Sasha.
So on your last slide, maybe you go. It seems like since you're talking about loops, the object on the left-hand side should depends on the IR cutoff, right? The amplitudes are infrared divergent. And so you mentioned that some of the divergence you could remove, but then I think you had the story of a drug where you said you cannot remove it. So is the idea that we should introduce this cutoff and it's physical and we should just restate everything as a function of this cutoff?
Okay, so several things. So first of all, what has been shown by Saha Sen was that the ratio of these amplitudes taking fully into account the long-range infrared interactions gives you, except for the log here, of course, infrared finite amplitudes. There were two types of divergences in the symplectic structure. One is a divergence in R, and one is a divergence in late time. So often, and this is true for superrotations at tree level, divergences in R you can subtract. The divergences in late time, when there are power law, as was the case also for scalar QED, which I didn't discuss in detail, but there was also a linear in time divergence, that you can subtract as well. But then logarithms, you cannot subtract. And the one in time was the one that multiplied essentially the charge, which has a conservation law. So, yeah.
Jack?
Is there a renormalization group improved version of this story which sums up the leading logarithms in that expression on your slide?
You mean an all-order statement here? What do you mean by just the leading one? Sums up?
Well, I keep turning it off. Well, I guess probably just the terms you've written. There are subleading terms with fewer powers of the logarithm compared to powers of omega. But the leading terms are the ones you wrote here, and the renormal, and in other contexts, the renormalization group sums those up.
Right. Yeah.
So the leading term here is 1 over omega. Then the next leading is log in omega. Then the next.
No, I mean that whole infinite sum.
Yeah.
Is what's called the leading logarithms, yeah. and the renormalization group resums that whole infinite sum in other contexts, not necessarily this one. And I'm wondering whether it's possible that it sums it up in this case as well.
Okay, I do not know that. Maybe to point out, while it is conjectured that this combination of powers of omega and log omega, so with these powers that are related, has been conjectured to be universal for this tower, but it has been explicitly proven to subleading order in the log. So I guess it's an open question whether this factorization property and the universality persists to all orders. And only if that is so, I think then you would have such a renormalization group statement.
Thank you. Andy?
The subleading soft photon theorem, of course, has been known since the 50s.
Yes.
Did it never come up, or it must have had it
I'm sure it came up in various discussions, so the tree-level subleading soft photon theorem has already been discussed in the context of symmetries, right, by Campiglia and Lada. And the symmetry interpretation was given, and it was also a large gauge transformation or superphase rotation that was divergent.
I don't mean the symmetry interpretation, just
yeah.
the theorem, there's a higher correction to it.
Oh, you mean the logarithmic correction, whether that never came up before. I guess not, but Ashok is in the audience.
Ashok,
maybe he can comment on
do you care to comment?
I haven't seen this discussion of log corrections earlier, because this is one higher order in the QED coupling, right? So if you look at the lowest order in QED coupling, you only have the tree-level soft theorem.
Yeah.
Okay. Anyway, maybe we should, sorry, Monica? Last
Just
one.
a quick question. So you talked about subtracting the various divergences from the charges. Do these subtractions, can they affect the positivity of the symplectic norm?
I think the a divergent symplectic structure doesn't really make sense. So that is my first problem that I need to solve, except for the logarithmic terms, which I cannot subtract if they depend on the matter content.
I mean, it could mean that your boundary conditions are too lax, and that's it.
Oh, okay. That's already true for superrotations. And in that case, okay, the relation to the soft theorem required the renormalization or the subtraction of divergent in R terms. I think it's also tied to the fact that symplectic structure is defined on Cauchy slices, but here we're really pushing it to the boundary. And then because we're pushing it to the boundary, there are divergences that appear. I would love to have a more, okay, so there's some ambiguities in the covariant phase space formalism, which allows you to subtract such terms. And I would love for there to be a principle that only allows specific terms. And I know that people are working on this and trying to find principles such that there's only specific terms that you can subtract. There are some ideas that you should only subtract local covariant counter terms and so on, but the full answer to this question is still an open one.
Okay, well, maybe we should conclude here. Thank you very much for a great talk.